Hello there, Virtual Precalculus. Well, I was informed by Ziggy that some of you are having trouble with the video 13.4 part 2, and so this is take 2, my second attempt at this video. I took out the first part, which was a funny video. Apparently, well, perhaps the problem has been that there was a copyright, some sort of copyright block. Anyway, I still want you to watch that funny part, and so I'm going to send you an email with a link to that video. It's not super important, but it is interesting and funny and relevant. So please watch that and then the rest of this video. And my initial comments following this segment right here are not going to make sense until you watch the video. So if you're confused, then pause the movie now and go check my email to you and watch the video that I point you to there. Alright, on with the math. Well, I don't know if you guys ever saw that show, but it was on all the time when I was a little kid. It was called Sesame Street, and that was The Count and the Cookie Monster. Anyway, that kind of counting is easy, but sometimes counting can be a little bit trickier than that. We're going to start off this section with just the fundamental counting principle. And you've seen it before in our MathMate probability and counting examples. We may not have called it this, but I think we did use it. If there are x ways to do one thing and y ways to do another, then there are x times y ways to do both. And here's an example that you've seen that uses this. Let's say we're making license plates, and we can use 2 letters followed by 3 digits. And if we're allowed to repeat, then the number of ways to find a letter, well, that's 26. So the number of ways to find 2 letters is 26 times 26. And then each digit, there are 10 possibilities. So to find the number of possible license plates, if we can repeat, we just multiply out 26 times 26 times 10 times 10 times 10. What if there are no repeats? Well, it doesn't sound like it would be that different, but because each choice takes one element out of the pool of further choices, it does make a difference. For example, the second letter, we only have 25 choices. The second number only 9, and the third number only 8. And so the number of license plates in a situation where we can't repeat 26 times 25 times 10 times 9 times 8. So things can change a little bit. You have to be careful to adjust the possibilities when there are or are not repeats. Sometimes this will be stated as replacement and without replacement. Replacement means the same thing as, you can repeat, and without replacement means you can't. All right, let's try a slightly more complicated example. How many ways are there to line 5 people up in a row? And the order matters. Who's first, who's second, who's third, fourth, and fifth? Well, how many choices do we have for the first spot in line? We have 5. Could be anybody. And then we've chosen that person already, so we only have 4 choices for the second spot, 3 for the third, 2 for the fourth, and 1 left over for the fifth. So the number of ways to do this is 5 times 4 times 3 times 2 times 1. That gets a special name in math. It's called 5 factorial, and it looks like this. That doesn't mean 5. It means 5 times 4 times 3 times 2 times 1, which is 120. Formal definition for a number factorial, for an integer anyway. N factorial is n times n minus 1 times n minus 2 times ... all the way down to 2 and 1. And another piece of that definition is that 0 factorial equals 1. Just believe it. It's true. Slightly modify that problem. What if we have 8 people and we're only going to line up 5 of them? Well, we would have 8 choices for the first, 7, 6, 5, and 4, right? And so this is what's called a truncated factorial. It's a factorial, 8 factorial, but it's been cut off below 4. The 3, 2, and 1 are gone. So we can think of it like this. 8 factorial divided by 3 times 2 times 1. Well, that itself in the denominator is a factorial as well. It's 3 factorial. So really what we have here is 8 factorial divided by 3 factorial. That gets another special name, 8p5. Or it's sometimes written as p bracket 8 comma 5, close bracket. The p stands for permutations. You use permutations when the order matters. We care who's first in line and who's second and who's third, etc. There's a different situation in which we don't care. When we don't use permutations, we use something called combinations. Anyway, permutations are different arrangements of things in which the order matters. In general, the notation NPR means n factorial divided by n minus r factorial. What if we're going to choose 3 of you guys out of your class of 7 and to make a group? And the order doesn't matter. It's just a group of 3 people, so we don't really care. There's no first, second, and third group member. You're just in the group or you're not. In that case, if we chose Fennu, Sumaya, and Sigrid, or Fennu, Sigrid, and Sumaya, or etc., 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 all 6 of these different possibilities are the same combination of U3. Okay, there are 6 different permutations that correspond to the same single combination of those 3 students, right? In any of those 6 possibilities, we have those 3 of you and we don't have the other 4. So they're all equivalent if the order doesn't matter. So if we wanted to count up how many groups of 3 we could form out of the 7 students in this class, 7p3 wouldn't quite do it because it would overcount. It would count each combination of 3 students 6 times, just like this combination was counted 6 times. So if we just divide 7p3 by 6, we get 35, and that's correct. That's the number of groups of 3 that I could form from this class. I could form 35 combinations. So why is there a 6 down there? 6 happens to be 3 times 2 times 1, which is 3 factorial. And that is because we have 3 people in each group. There are 6 ways to permute a list of 3 names, okay, as we saw up above. All right, so 7p3 divided by 3 factorial, or 7 factorial over 4 factorial. The 4 comes from 7 minus 3, remember? And then also over 3 factorial. This is called 7c3. Or 7 choose 3. Okay, another special notation, the C stands for combinations. NCR, or C of n comma r, or just this funny bracket NR, is defined to be n factorial over n minus r factorial over r factorial. Combinations, when order doesn't matter. Here's some examples to test whether or not we understood that. Let's say we have 4 letters and 4 envelopes. And we randomly put the letters into the envelopes. We just close our eyes and do it. What's the chances that we get each letter in the correct envelope with the right address on it, right? Does the order matter? Yes. I mean, the order is really all that does matter. We got to get the right envelope around the first letter and the right letter inside the third envelope, etc. So it's a job for permutations. Of 4, we're choosing 4. So 4p4, this turns out to work out to be 24 ways. So the chances of getting it right randomly are 1 out of 24, or 4%. Example 8. We're going to have to discuss it in part 3. This video is already getting too long. But it's basically a lottery where 54 balls each have a unique number on them, and we're going to pick 6 and try to get them right. See you in part